Here is a game. There are 3 doors. Behind one of them is a car. Behind the other 2, for reasons no one ever explains, is a goat. You pick a door, let's say door 1. You don't open it yet. Right now, your odds of having picked the car are exactly 1 in 3. Simple enough. But the host knows what's behind every door. And instead of opening yours, he walks over to one of the doors you didn't pick, and opens it, to reveal a goat. He will never, ever open the car. Now he turns to you and makes an offer. 2 doors are still closed, your original pick, and 1 other. You can stay with door 1, or you can switch. And almost everyone says the same thing. 2 doors, 1 car, it's obviously a coin flip. 50-50. So why bother switching? Except it isn't a coin flip at all. To see why, go back to your very first pick. 1 time in 3, you pointed straight at the car. But 2 times in 3, most of the time, your very first pick was a goat. And here's the trick. Every single time your first pick was a goat, the car is behind the other closed door, and switching hands it straight to you. So switching wins in exactly those cases, the 2 and 3 times your very first guess was wrong. Stay, and you only win the 1 and 3 times you were right at the start. That's the whole secret, and for 50 years, it has started arguments. The reason your gut is wrong comes down to one fact about the host. He knows where the car is, and he will never open it. So his choice of door isn't random, it's a clue. To see it, let's just be stubborn and list every possibility. You always pick door 1. The car is equally likely to be behind door 1, 2, or 3 cases, each 1 in 3. Case 1. The car is behind your door 1. The host opens a goat, you switch, and you hand away the car. Here, switching loses. But case 2. The car is behind door 2. The host can't open your door, and can't open the car, so he is forced to open door 3, and switching wins. Case 3 is the mirror image. So switching loses in exactly 1 case and wins in the other 2. That's 2 times in 3, the same answer, now with nowhere left to hide. In 1990, a reader sent this exact puzzle to Marilyn Vos Savant, who wrote the column Ask Marilyn in Parade magazine. She answered correctly, you should switch. And then the mail arrived. She received around 10,000 letters telling her she was wrong. Roughly 1,000 of them came from people with PhDs, mathematicians and statisticians whose entire job was being right about exactly this. One reader wrote simply, "You blew it." Another informed her, "You are the goat." A math professor said he was in shock that she still couldn't see her mistake. She was right, and all of them were wrong. She held her ground and walked through it again, and one by one, classrooms that actually simulated the game watched switching win, and came around. Even Paul Erdos, one of the most prolific mathematicians who ever lived, refused to believe it, until a colleague sat him down and showed him a computer playing the game hundreds of times. If the proof still feels like a sleight of hand, there's a way to settle it that uses no theory at all. Build the game, play it thousands of times, and simply count the wins. Run 10,000 games where you always stay. You win about a third of them, somewhere near 3,300. Exactly the 1 in 3 you started with. Now run 10,000 where you always switch. You win about 2/3, around 6,600. Twice as many cars, for the price of changing your mind. And the more rounds you play, the more tightly the results lock onto 1/3 and 2/3. This is not a rounding artifact. It is the genuine shape of the game. Here's the version that finally makes it obvious. Same rules, but now there are 100 doors. 1 car, 99 goats, and you pick a single door. Your one door has a 1 in 100 chance of being right. Which means 99 times out of 100 the car is somewhere in the pile you didn't choose. Now the host, who knows exactly where the car is, opens 98 of those other doors, every single one a goat, and leaves just one other door closed. 2 doors remain, your original 1 in 100 guess, and the one door he very deliberately chose to leave standing. Does that still feel like a coin flip? All 99% has funneled onto that one surviving door. Switch, and you win 99 times out of 100. The 3-door game was always just this, whispered. We've counted it, simulated it, and stretched it to 100 doors. Now let's prove it cleanly in symbols. Call Ci the event that the car is behind door I, and H3 the event that the host opens door 3. Before anything happens, the car is equally likely to be behind any door. So the probability of each one, C1, C2, C3, is exactly 1/3. Here is the crucial part, the thing your gut quietly skips. If the car is behind your door, the host is free to open either 2 or 3, so he opens door 3 only half the time. But if the car is behind door 2, he is forced to open 3. And if the car is behind door 3, he can't open it at all. His hand is forced, and that asymmetry is the whole secret. Feed those into Bayes' theorem. The chance the car is behind door 2, given that he opened door 3, is the 1 times the third on top, divided by every way door 3 could have been opened. Work it through, and it comes out to exactly 2/3, the same answer the doors, the simulation, and the 100-door version all gave you, now nailed down in algebra. And once it's in symbols, you get something the doors alone can't give you, one formula for any number of doors at all. Call that number n. Your very first pick is right with probability 1/n, which is tiny, when n is large. So the car is in all the rest, with probability n-1/n. The host clears away every goat but one, leaving all of that on the single door he keeps closed. Set n to 3, and you get 2/3 our game. Set n to 100, and you get 99%. The same formula, all the way up. And as the doors multiply, that number races toward 1. With enough doors, switching is nearly a guarantee, and staying is nearly a tragedy. One last way to feel it: imagine playing this game not once, but 300 times in a row. Stay every single time, and you drive home with about 100 cars. Switch every single time, and you take home about 200. Same doors, same host, same one decision, and twice the cars, for nothing more than overruling your gut. That's the entire prize for trusting the math over the feeling. The secret was never really about the doors. It was about the host. Because he knows where the car is, every door he opens is a clue, and he quietly hands those clues to the other door, never to yours. So switching isn't swapping one door for another. It's trading your single first guess for every other door combined, with all the worst options already cleared out of the way. And that's a habit worth stealing. When real information arrives, from someone who genuinely knows more than you, the smart move is to update your choice, even when your gut wants to sit perfectly still. There's an entire branch of math built on exactly that: how far your beliefs should move when the evidence shows up. It's the same reason a positive medical test can still mean you're probably fine, but that's a story for next time. The 3 doors are enough for today. Your instincts are fast, and they are confident, and, about 2 times out of every 3, right here, they are completely wrong. So when the host opens a door, and turns to you with a smile, and asks if you'd like to switch, now you know the answer. Say yes.